Hello, my name is David Basil, and this is a presentation for the Pavement Renewal, Rehabilitation and Reconstruction Unit for the University of Tasmania and Centre for Pavement Engineering Education. This is the major design assignment, and it's titled Rehabilitation Design Project. This design project presents a review of design and performance data to determine a recommendation for a maintenance and rehabilitation strategy for the inner and outer westbound lanes of a dual carriageway that will minimise the whole of life costs for a 20-year design life. It is proposed to structurally rehabilitate the two lanes, the outer and inner, of the westbound carriageway of the 4-lane Deer Park bypass in Victoria. The west and eastbound lanes are separated. The section under consideration is 3.5 kilometres long with traffic lane widths of 3.5 metres for each lane, which is 7 metres trafficked westbound carriageway, plus a 1 metre wide sealed shoulder of 40 millimetre thickness asphalt on the outer and inner lanes. The original pavement design was based on a design traffic loading of a equivalent standard axles ESA of 2 million, or 2 times 10 to the 6, and the current pavement structure is in the table below. So starting from the bottom of the table, there's a clay sand with a CBR of 7%. Then there's 300 mils of select fill, and on top of that there's 200 mils of granular subbase, and on top of that is 175 granular base course, and then 75 millimeter of asphalt leveling course, and a 50 millimeter wearing course of asphalt. Based on the roughness measurements provided for say chainage 3200 to 3500 along the inner lane, and changes 3100 to 3500 along the outer lanes, they require some intervention of rehabilitation because the IRIs are 4.83 and 4.85. If you look at the table, it should be less than 4.2. The next slide shows indicates that the design deflection for design traffic for 2 times 10 to the 6 ESA for the inner lane and 4 times 10 to the 6 ESAs for the outer lane are estimated to be, if you look on the graph there, it's 1.06 millimeter and 98 millimeter respectively. Based on the roughness index and deflection measurements, structural pavement strengthening or overlay treatment is not required for most of the road section, except for changes 3200 to 3500 metres along the inner lane and changes 3100 to 3500 along the outer lane. As the subject treatment area is closer to the saltwater bridge, it is recommended the section between 3400 and 3500 metres should be fixed at the same level. Even though the structural overlay is not required for changes 0 to 3200 along the inner lane and changes 0 to 3100 along the outer lane, a thin asphalt overlay of 30 millimeters can be considered for reshape the pavement and improve riding comfort. Based on the above estimation, an overlay thickness with a C320 binder can be adopted at as 50 millimeters for inhibiting permanent deformation. The next slide shows that for overlay asphalt for fatigue life, the overlay thickness is the 110 millimeters for the inner lane and 130 millimeters for the. An alternative overlay treatment would be to use an asphalt mix with an A10E binder from 6.10 for overlay using an A10E asphalt mix at a weighted mean annual pavement temperature WAMPT of 25 degrees Celsius. The overlay adjustment factor is 1.07. Therefore, the asphalt overlay required to strengthen the pavement is 50 times 1.07 equals 53.5 millimeters, which can be rounded up to 55. For inner lane, the adjustment factor to the fatigue life due to the use of an A10E asphalt mix is 3. Consequently, the revised fatigue life for the A10E overlay is 3 times 1.0 times 10 to the 6 equals 3 times 10 to the 6 ESA, which exceeds the traffic design loading of 2 times 10 to the 6 ESA, and so a 55 millimeter thick A10E overlay is satisfactory compared to the 110 millimeter of C320 dense grade asphalt. For outer lane, the adjustment factor to the fatigue life due to the use of an A10E asphalt mix is 3. Consequently, the revised fatigue life for the A10E overlay is 3 times 1.4 times 10 to the 6 equals 4.2 times 10 to the 6 ESA, which exceeds the design traffic loading of 4 times 10 to the 6 ESA, and so a 55 millimeter thick A10E overlay is satisfactory compared to the 130 millimeter of a C320 dense grade asphalt. The following pavement methodology can be adopted for the inner lane. Remove the existing pavement layer to 155 millimeter depth and then place asphalt layers. Now, the following pavement methodology can be adopted for the outer lane. Remove the existing pavement layers to 180 millimeter depth and then place the asphalt layers. The following pavement methodology can be adopted for the inner lane. Remove the existing pavement layers to 175 millimeter depth, stabilize the existing granular material to 180 millimeter depth, place asphalt layers. The following pavement methodology can be adopted for the outer lane. Remove the existing pavement layers to 175 millimeter depth, stabilize the existing granular material to a 200 millimeter depth, and then place the asphalt layers. The following are assumed for the initial pavement rehabilitation cost estimation. 30 millimeters non-structural asphalt overlay has been proposed for C chainage 0 to 3200 inner lane and chainage 0 to 3100 outer lane traffic lanes. Shoulder treatment is not considered for chainage 0 to 3200 inner lane and chainage 0 to 3100 outer lane. A 55 millimeter thick structural overlay for chainage 3200 to 3400 inner lane and 3100 to 3400 outer lane traffic lanes plus shoulder. A 40 millimeter mill and overlay has been considered for changes 3400 to 3500 inner lane and changes 3400 to 3500 outer lane shoulders. The following are assumed for the ongoing pavement rehabilitation cost estimation. Routine maintenance is proposed every year for traffic lanes plus shoulders. A 40 millimeter mill and overlay has been considered for entire traffic lanes plus shoulders in 10th year and 20th year, and a 10% patchwork for the total area of the traffic lanes has been assumed for patchworks in the 5th year. The following table summarises the life cycle cost comparison for Alternative A and Alternative B based on the discount rate of 4% and design life of 30 years. So based on the two options, Alternative B has the lesser present worth than Alternative A. Hence, adopting overlay plus base stabilisation method would provide an economically viable solution. Thank you.